Hi, welcome to the Decarb Connect podcast. And today I'm very pleased to be joined by Jeffrey Rissman, who is the Industry Program Director at Energy Innovation. And we're going to be talking about both some of the policies and types of policy design that could help underpin commercially competitive decarbonisation in the US. So, Jeffrey, perhaps I could ask you to start by giving a bit of an intro to you and your background and how you've arrived at this moment in time.
Sure. Thanks, Alex. I'd be happy to. And thanks for having me on the podcast. At Energy Innovation, I'm focusing on how to decarbonize the global industrial sector across all different industries. Prior to this at Energy Innovation, and still ongoing, I work building a tool called the Energy Policy Simulator. It's a large open source computer model that can simulate all different parts of the economy, the transportation sector, the industry sector, the buildings, appliances, electric power. It's free and open source, and it's available for multiple countries and regions. It was actually my experience working on that tool that sort of led me here, because one of the things that kept emerging when I would look at the results and outputs for different countries is that the industry sector is responsible for a huge share of the energy use and especially the emissions, including process emissions, which I'll talk about later. And it sometimes is overlooked. You know, people think about there are ways to decarbonize the transport sector, like electric vehicles or good urban design that facilitates walking and biking and public transit, or electric power with solar and wind and batteries and interconnecting larger balancing areas, or buildings with smart thermostats and green design, good insulation, rooftop solar. And there just is less awareness of the solutions that focus on industry, even though the need is so great. So I still work on that computer program, but I shifted over to have the majority of my work be on finding technologies and policies that will decarbonize industry.
Talk to me about your perspective, or not just yours. You know, what does the data tell us of the three top emitting industries, and what are some of the issues that sit there, just to give some context to then what we'll go on to talk about?
Absolutely. That sounds great. So one thing about the industry sector is that the emissions are concentrated into a small number of industries, especially the top three. Those top three, including energy-related and process emissions, are chemicals, which includes making the basic input chemicals like petrochemicals like ammonia and methanol, and then downstream chemical products, of which there are many thousands. So that's chemicals. The second one is the iron and steel industry. And then the third is cement, the main ingredient in concrete, the binder. I mentioned energy-related and process emissions, and it's probably good to give some background on that at the moment, because I'll be talking about how to decarbonize both. So energy-related emissions just means when you're burning fuels for heat or power motive force, so combusting natural gas or coal or biomass or any sort of combustion. And of course, electricity, if you're using that, will also be for energy and doesn't generate emissions where it's used. It generates emissions possibly where the electricity is made. The process emissions are we're talking about greenhouse gas emissions here, are emissions from industrial processes other than combusting fuels for energy use. So a good example is when making cement, you have to chemically break down limestone, which is calcium carbonate, CaCO3, to lime, or calcium oxide, CaO, and carbon dioxide, CO2. So the CO2 there is coming out of limestone. It's not coming out of a fossil fuel. And then you use that calcium oxide, the CaO, goes into making clinker, which then is the main component of cement. There are also non-CO2 process emissions. The most prominent are fluorinated gases produced by the chemicals industry and used as refrigerants and aerosol propellants and things like that. process emissions are one reason why the chemicals industry and the cement industry are so high up there. A good share of their emissions, those two, are process. With iron and steel, there are process emissions also, but most of their emissions are energy related.
Yeah, it's an interesting one. I think most of us in our day-to-day lives are so divorced from how these critical materials, the foundational materials of how we live, what we drive, the buildings we live in, but we're so divorced from actually how they're made. It can sort of feel quite incredible when you hear about the amount of what the proportion of CO2 is that comes from those sectors. So I think I know off the top of my head that the often quoted stat for cement is that it's 8% of global CO2, give or take, and something similar for steel, I believe. Can you flesh that out at all?
Yeah, so those numbers sound about right to me. Different sources actually vary by 1% or 2 that I've seen, because they count different things. With iron and steel, do you count upstream emissions in making the coke that goes into the blast furnace, say, or is that part of a coke making sector? So depending on where you draw the system boundaries, it can vary a bit. But you're right, it's about 8%-ish, and these data are from 2017. You have 57% of industrial emissions are from the top 3 industries, the 3 we mentioned, and the top 10 industries account for 83% of industrial emissions. After those top 3, the next ones are non-ferrous metals, primarily aluminum, is 4, refining is 5, food and tobacco processing. That's not agriculture, by the way. That's taking the outputs of agriculture and cooking it and packaging it. It is next, then pulp, paper, and printing, and then forming machinery from produced metal, and so on down the line. So one thing about industrial emissions that makes them more tractable is, although there are many industries out there, you don't have to, you can get outsized benefits, outsized decarbonization benefits by focusing on a small number of them, the top 3 or the top 10.
Okay, so let's move. We've got those sectors in mind. Let's then have a look at the main ways. Again, this is kind of still scene setting, really, but I think it's useful to look at the main tools and types of technology that are viable for those sectors to consider. So if you're just going to give an overview of those, obviously we'll look at a particular industry and dig into this a bit more. But what's the overview that you would give on, okay, these are the buttons, these are the levers, what have we got at our disposal that feels like a realistic and viable route for these industries to consider?
The way I characterize it in my mind is there are cross-cutting technology options that are very powerful and that can be used to help decarbonize most industries. Maybe all industries can use these technologies to some degree. And they are energy efficiency, electrification, hydrogen, and demand side interventions like material efficiency and circular economy. And I'll say a sentence about each of those, and we can delve into them a bit more. But then aside from those cross-cutting technologies, those 5 or so groups that I mentioned, there are specific technologies for the top 3 industries that are worth considering. So there are ways to decarbonize chemicals production that are pretty specific to the chemicals industry. So examples might be biomanufacturing or improved chemical catalysts, or various ways to replace chemical feedstocks with zero carbon feedstocks. So some of those things might not be applicable very broadly outside the chemicals industry, but are still very important for industrial decarbonization because the chemicals industry is important. And steel has some of its own, like molten oxide electrolysis, or doing direct reduced iron using zero carbon hydrogen instead of natural gas or coal. So, but to go back to the cross-cutting ones, I'll say energy efficiency is seems straightforward, but you have to remember it's not just about the components, like having an efficient individual electric motor inside your conveyor belt or an individual efficient boiler. It also is about how you build the entire industrial system and how you put all those components together. So you can have the most efficient boiler in the world, but if the produced steam is used inefficiently, you still might be having not great overall energy efficiency from energy to the final produced product. And there are opportunities there to perhaps replace steam with something that targets the energy more precisely at your need, whether that's lasers or numerous other options, inductive heating, dielectric heating, and so on.
An interesting one that I think kind of comes alongside that, even though it's a different type of technology, is I suppose the data processing and business decision support data that can be generated. I don't know about you, but I hear more and more about solutions in that space, and how even kind of relatively easy kind of changes in the data you collect and how it's processed, and the decision-making time can then reduce, can reduce your kind of overall output of emissions by just making better decisions based on better information quicker. And I guess these, like energy efficiency in general, and I guess those data tools, fit into this sort of what we can do right now kind of bucket, right?
Absolutely. Yeah, we don't need new technology breakthroughs to access these R&D, these energy efficiency improvements, especially when it comes to these ones about how you fit the components together, or better use of data and business intelligence. One granular example might be using information about the flows of materials or through your system to purchase more appropriately sized components. And so, if you have uneven material flows, let's say you have a very large pile of material, then on the conveyor belt, then nothing, then a large one, then nothing, or a large pumped amount of fluid and then little, and then large and then little. You need a large pump or a large robot arm to move the material, and then much of the time it's idling. So you have this thing that's working, that's built to, and it saves money also to not do this. So you have a thing that's overbuilt with more capacity than it needs, and then it's only used sometimes, which is not the most energy efficient way. The most energy efficient way would be to have many smaller piles of material, or a more constant, smaller flow that you can then handle with a smaller pump running at its optimal design capacity. And that can often be a matter of information and flowing through the system that helps you design around that. If variability is unavoidable, you can do something like have 3 pumps and start up only as many of them as are needed to handle the material flow at any given time, rather than running one enormous pump at 1/3 of its intended design capacity. Another promising cross-cutting technology is electrification. So when you're looking at industrial energy use, some is already electricity. The rest is combustion, mostly fossil fuels that are burned on site in an industrial facility. And the vast majority of that combustion energy, about 91% of it, goes to make heat. So that's excluding feedstocks. So a lot of the fossil fuels used by industry, particularly in chemicals, are feedstocks. But excluding those, 91% of the rest goes to making heat. Much of that is to heat boilers to make steam, and the rest and a lot of the rest is other process heating, all kinds of different industrial processes, like melting metals or driving chemical reactions where you need to add energy to get the reactions to go, endothermic reactions, and so on. So a lot of what electrification comes down to is creating heat from electricity at the required temperature and in the required quantity for industrial uses. And there are lots of promising industrial technologies that can do that, too many for me to get into. I'll just mention that at low temperatures, meaning about up to 150, 165 degrees Celsius. Heat pumps are the most efficient way to go, and can be several times more efficient than electric resistance heaters because they don't have to create the heat. They just have to move it from place to place. And then for higher temperatures and other applications, you have electric resistance heating, electric arcs, which are used in electric arc furnaces and arc welding. You have induction and dielectric heating. Dielectric heating is like what happens in your microwave oven, but can also be done with radio waves. Infrared heating, and then targeted things like lasers or ultraviolet light can avoid the need for heat, let's say for curing epoxy adhesives or coatings. So there's lots of opportunities there that cut across almost every different industrial need. And cost is the main, so it's not so much physics that's a limit there, but cost, because electricity is more expensive for creating heat, particularly at temperature ranges higher than can be served by heat pumps. So you don't get that huge heat pump efficiency benefit. That can be overcome in various ways. One is by observing that sometimes the heat is used inefficiently, like the inefficient use of steam that comes out of an efficient steam boiler. And then policy can help as well as declining costs of electricity with deployment of renewables like wind and solar, which are now the cheapest way to get electricity in many parts of the world. I will say that I do believe the grid will be decarbonized sooner than industry will be. And so electrification doesn't have to wait. I would say to industry, if you want to decarbonize industry, you don't have to worry yet about so much, especially in the US or Europe, about whether the grid is decarbonized yet, because it's getting there, and it's getting there faster than many other techniques like using hydrogen will get there. So if you electrify, even if there's still some gas plants or whatever on the grid, I think that's okay, and they're going to be transitioning off for policy reasons and price reasons. So that I think is very encouraging.
So simply moving to more electrification, even if it isn't in the very short term of a kind of carbon neutral variety, isn't necessarily an impediment to the long-term gain that it might present to a business.
Exactly. I mean, you can figure out what the share of decarbonized electricity on the grid is. There are even utilities that let you pay or to buy dedicated decarbonized electricity, which you can absolutely do. But even if you don't, even if you just electrify and use grid electricity, that still is going to help get us there to a fully decarbonized industry sector, because that electricity will become decarbonized quicker than people expect. So I think that's an encouraging thing.
So then hydrogen is on this hit list.
Yes, hydrogen is useful for a lot of different industries.
But also kind of well, I don't know, it gets a real, I guess along with CCUS, has a lot of shouting both for and against, doesn't it? There's a lot of kind of massive advocates who lobby for the power of hydrogen as a fuel and all kinds of things, but also many who just keep pointing to cost. So what's your, tell us a bit about partly the use, but also what's your view on that argument and what it means for industrials?
So you're right that there's a lot of different thinking about hydrogen these days. The hydrogen is already used to a great extent in industry, and a lot of the processes that use it, say in the chemicals industry to produce ammonia, are technologically mature and widely deployed. The thing is that the hydrogen is generally not produced in a zero carbon way. Most of it is produced by steam reforming of methane. So hydrogen can be produced in a zero carbon way, though. The most common way that's done today is by electrolysis. So you run an electric current through water, and it splits those H2O molecules into hydrogen, H2, and oxygen, O2. And then if that electricity is decarbonized, or as we were just talking about, if it will be, soon, the 2030s, you can have low carbon or zero carbon hydrogen coming in, and then you can use that either as a chemical feedstock And it's a very promising feedstock for lots of different chemicals. Or you can use it for energy. So you can burn it and combust it kind of like a fossil fuel, and it will heat, it'll provide that industrial heat. And you can do things with it that you would have done with a fossil fuel. So you can capture waste heat, you can do all the usual stuff. The challenge with hydrogen, I guess there are two. One is that at the moment it's still more expensive to produce zero carbon hydrogen than it is to buy fossil fuels and burn them per unit energy, or to use them as chemical inputs, even with steam reforming of methane. So part of it is price, and that can be dealt with partly through improved R&D, driving down the cost of hydrogen technology, partly through policy. So things like clean energy standards or carbon pricing can help level the playing field by internalizing some of the costs and damages that are caused by fossil fuels that are not being paid now by the fossil fuel users. So part of it is cost, and the other part is that some amount of changes to the equipment are going to be needed to use 100% hydrogen.
What's your gut feel as someone who's obviously analyzing data around this all the time, I imagine, and talking throughout your networks to people about this? What's your gut feel on the kind of timeline to more industrial application of hydrogen?
Good question. Hydrogen, and it depends on the application. So for feedstocks, it's a little closer in, and for burning it for heat, that's a little further away. I do think that for switching over to hydrogen for heat and such, we're at scale, we're talking about some decades away, still before 2050. So still in a relevant time frame for decision makers today, given the long lifetimes, decades long, of industrial equipment. So that's not to say don't think about it yet, but it's to say that hydrogen uses is not the first thing that will for heat is not the first thing that will be deployed at scale. It'll come in sooner, well, you could start, of course, with processes that are already using hydrogen and just swap green hydrogen for hydrogen produced through steam methane reforming or coal gasification. So that's the most straightforward substitution. And then there are other chemical pathways where you can use hydrogen and things where, let's say, steel making, where it is being used for heat, but also you can use it as a chemical reducing agent, which means it takes oxygen atoms from iron oxide to leave behind the iron atoms, metallic iron. So where you're using it for a purpose like that, there's a little more economic incentive to transition to hydrogen quicker than just for bulk heat. And also electrification isn't as much of a competitor when you're talking about the use for iron and steel and for chemicals, because you need the chemical properties, whereas for bulk heat, there are going to be electrical technologies that might supply some of that. So that's why I think that the closest in thing, I mean, they can start substituting clean hydrogen for fossil hydrogen right now in applications that are already using hydrogen, and then in more chemicals in iron and steel, and then 15, 20 years for heating, where it makes more sense than electrification or carbon capture. The opportunities for these technologies, so it's a bit different for each one. So let's start with energy efficiency. So the opportunity here varies a lot globally because different industries in different places have already either achieved fairly good levels of energy efficiency or are fairly poor performers. So in some countries that are significant industrial producers like India, there's not a lot, the average level of energy performance in a lot of industries may be low, and there may be a great deal of opportunity today to sub in more efficient best practice technologies. In other places, the US and Europe, the average level is higher, especially at the component level, but there still are opportunities to do some of those system-wide swaps or configuration changes where you're trying to optimize the performance across the whole facility or multiple facilities. You mentioned that some decision makers in industry might see this as a cost. Usually, energy efficiency improvements are one of the most cost-effective investments because they pay for themselves in a fairly short amount of time. They have a good rate of return. They can be overlooked anyway, and the main reason for that is not because their rate of return on a percentage basis is poor. It's not, it's good. The reason is because the absolute quantity of dollars may be small. And that's because energy input is often one of the smaller input costs for many businesses. It may only account for a few percent of their expenses. Whereas if you're looking at costs like staffing or buildings or marketing or the numerous other things industry pay for, they're larger percentages. And so industries, of course, they look at rate of return, and energy efficiency performs very well on that metric. But they have limited amount of staff time and limited amount of decision-making power and places the executives can focus their attention. So sometimes a business might opt for to do something with a 5% rate of return on 10 times as many dollars rather than an 8% rate of return on just 1 times as many or 1/10 as many dollars, because you end up with more dollars even with the lower rate of return. So if an industry had infinite attention span or could divide its attention ideally, with its staff time, they could pursue all of these things in order from highest to lowest rate of return. But there are just sometimes decision-making constraints there, which gets back to your point earlier about business intelligence. We talked about how it could factor into a small-scale decision like how many pumps you get and what size, but it can also factor into large-scale decisions like this. Like better business intelligence could maybe allow you to focus more exactly on the highest rate of return projects, and some of those will be energy efficiency. Electrification, I can go on to electrification now if you like.
Yeah, it was circular economy that I wanted to pick up on, because I think it's an interesting idea that people in abstract can understand. Kind of feels more about business opportunity rather than talking about savings reduction. It's about a future business momentum, right? But also perhaps hard in some of these hard to abate sectors to quite conceptualize or imagine what circular economy applications could emerge. And I just wondered if you could talk us through that, like just a couple of examples, like what sorts of things are really seemingly possible as kind of, that could be interesting as circular economy.
I'll be happy to talk about circular economy. So first, just to define it a bit for any listeners who aren't familiar with it, the idea behind circular economy is to put each product or material to its highest and best use at each point in its life cycle. So you let's say you have a product, a car, say. Maybe it's an electric car, and the highest and best use of the car is to keep it in service for longer. So the first option would be of circular economy would be longevity and repairability. So if the car is designed to be easily repaired and designed to be robust and not break down quickly, then it can last for longer, even with the first owner. And then you can transfer to new owners, so that might be considered sort of a second tier. So if the first owner is done with it, you could transfer it, reuse, redistribute it. Then if it needs work, the third best option would be to sort of refurbish it or remanufacture. Remanufacture means you take the components out and reuse some of the components in a new product. And then if that isn't possible, so the product is obsolete or something, recycling would be sort of tier 4. So you break it down to component materials, and then you use the steel from the car to make new steel in an electric arc furnace, and so on. And then hopefully it's not downcycling, which is recycled material but at a lower grade, but some of that can be. So it's hard to make everything fully circularized, usually beyond tier 4. Usually there's some stuff you can't recycle and that ends up turning into waste. So part of circular economy is trying to minimize that. But one thing we also have to pay attention to is the energy use involved in each step. So recycling isn't zero energy. So you need to think about that and make sure that it's decarbonized energy or otherwise makes sense. Some of the first better options are zero energy, like transferring it to a new user, like selling a used car, say. So here's one example of why there's a lot of potential for better use of products. So the first tier option in circular economy is longevity, but it's also making better use of the products that exist, because if more people are able to use the same product, you don't have to manufacture two of them. So one example is that in the United States, the average light duty vehicle, so that's a car or an SUV, is used for about 6 hours per week to carry about 1.4 people at a time. That's from US National Transportation Statistics publication. So it's clear that a lot of light duty vehicles are spending most of their time parked. And you don't need nearly so many light duty vehicles to meet the need for transportation services. And so if you have systems in place that allow the vehicles to be used more efficiently, whether that's a car sharing system or whether that's a public transit whose vehicles have higher utilization percentages by more people at once, that can play into the first tier of circular economy up there with longevity.
I think that plays into something we have talked about on a podcast before, where one of the it was a UK company called Celsa, who operate a steel company that operate electric arc furnaces. That's their process. But they were sort of talking about the ideas of steel as service, which would play into the idea of car as service in a way, wouldn't it? I think that kind of business model where the original materials company, the company that then processes and produces the next stage on, are actually incentivized. Their business model incentivizes longevity, because they're going to keep recouping, keep bringing back into service that material or that product. I hope I sort of explained that in a sensible way, but I find that concept, which kind of plays into this better use of products as well as longevity, kind of really interesting. Like steel as service as a future business model. I don't know how conceptually easy that is to move towards, but it's certainly an interesting idea.
It sounds fascinating. I don't actually know what exactly they had in mind, but I agree that if you bring in more industrial products as services, then the companies that are providing those services are going to have a strong business incentive for longevity, because they retain ownership of the vehicle even as it's loaned out to person after person, or whatever it is the product. Maybe they're loaning out use of an electric arc furnace, or they're loaning out use of a piece of industrial equipment, which may make sense across industries, where there are some processes where an industry might occasionally need to use certain type of machine, but not constantly every day. And so avoiding having to buy their own whatever it is, huge furnace or such, might make a lot of sense. Maybe that's the analog of a sort of sharing model for industrial equipment. And then the company that's loaning out that equipment wants to get the furnace or the piece of equipment with the best longevity possible. So they're going to be pressing manufacturers to produce extremely durable, long-lasting, repairable electric arc furnaces in this example. And so the manufacturers will respond to that need and produce what the buyer demands, the type of furnace the buyer needs. So I do think there's a good route there for aligning it with business incentives.
Well, let's, if it's unless I'm kind of interrupting flow, how about we move into looking at how do we actually support these things? So you've talked through these kind of key areas of technology that can apply to a range of industries. You've also mentioned some of the specific examples. You used the chemical sector, kind of looked at very specific examples of biomanufacturing and improvement of chemical catalysts as a way that they can very specifically improve and reduce emissions. Let's now turn our attention a bit to what needs to happen to make those viable. So we can ask industry to do things, we can point at the tools and technologies, but we still need some kind of support, right, to get through this transition phase, which is uncomfortable and potentially expensive. So how do we do that? What's needed to get us through this kind of transition phase?
You're absolutely right that support is essential. And here I'm thinking of government support, government policy. So government has played a huge role in the development of energy and industrial technologies we use every day, whether that's through the space program and defense funding or aeroderivative turbines. There are many examples, and so the one area we can look at is what companies need to optimize R&D, so to get the new technologies out there. Then the other sort of area is how do we level the playing field and make sure the financial incentives are there to scale up and deploy these new technologies across the industry. And for that, we'll be looking at things like standards, which can be energy efficiency standards, emissions standards, and in some cases, perhaps even material efficiency standards. I'll speak briefly about each of these in a moment. And then there's carbon pricing, which is also a powerful option. And then there are some other policies that can be supportive. Green government procurement, for example, can create a starter market to help some of the new processes scale up, which drives down their costs, which then allows them to access a larger market, which drives down their costs further, and so on. And then data disclosure, labeling requirements, and so on. So just to go kind of in order, I'd like to start with R&D support, because it's not the first type of government policy many people may think of, but it's valuable. So governments can help private firms better aim their R&D at important societal needs like decarbonization, and accomplish it at lower cost and with better rate of return. So there are lots of methods. One, of course, is directly funding that R&D, so the government can do research grants or contract research for the government. Another is they can do cooperative research and development agreements. So a government lab, like a national laboratory, might partner with a private firm to research a topic that will help that firm improve its manufacturing processes. And or the government can make its labs available sort of for hire to work with some of the engineers from the private companies on questions of importance to them and that the government cares about. A good example is in the United States is I think it's Sandia National Laboratory has an ignition facility that does research on combustion, and they can partner with engine makers. So it may not, if you're an engine making company, it may not make financial sense for you to build your own ignition laboratory and hire career staff who have deep knowledge of the relevant physics, because it's so expensive. And the improvements to your products, while real, may never recoup the costs of building your own national laboratory equivalent. But if you can simply work with the existing one and pay for a little bit of their time, that can be a worthwhile R&D investment that has a good rate of return on it in improving your engine efficiency.
And to be clear, this is a model that is not just, this isn't just about climate and climate issues, is it? It's a well-trodden path that there are plenty of examples of over the last few decades of all kinds of commercial activity that originated, or at least were supported by this kind of R&D program.
Yes, it's been used for all kinds of collaborative R&D into all kinds of things in industry, whether that's public health or safety of products or energy efficiency or innovative new processes. Absolutely. In this case, though, it would be good for governments to earmark some amount of the national lab's time or funding to projects that do improve energy efficiency and lower emissions, because decarbonization is such an urgent problem to protect humanity from devastating climate damages. So there is a reason for governments to consider prioritizing some of their R&D support to that need. But you're right, it's certainly not exclusive to that need.
So emissions standards then, which I know in probably every country is a bit of a political hot button, isn't it? But tell us about this as a mechanism that could help industry.
So emissions standards are ways to help they do a few things. They can get the least worst performing products off the market. So sometimes there are misaligned financial incentives where, one person is buying the technology and another person is operating it. And so the person buying the technology might want to get the cheapest unit, and the one operating it wants the most fuel efficient one. You see this a lot in buildings, say, where there might be a landlord-tenant relationship and the tenant pays the energy bills and the landlord buys the appliances. So they end up buying the worst performing ones that use the most energy. That type of incentive mismatch is less common in industry than in buildings, but can still happen in various ways due to things like short-term planning horizons, the need to show good financial results quarter after quarter for investors who may not be looking 20 years out over the lifetime of a product of a machine, or financial constraints today. So there are certainly reasons why industry may sometimes opt for a cheaper machine up front. And standards can help by removing some of the worst performers. They can also provide financial return for companies that do invest in improving their products through R&D by helping them gain market share. If you care about R&D, if you see yourself as technology focused, you're the type of business that can often gain from tighter standards on your products by helping you get a leg up on the inefficient competitors. So that's a different way that standards can help.
And carbon pricing, obviously one that has been getting a lot of airtime recently. So just sort of in brief, like what do you see? Tell us a bit about what you see coming down the track for this in the States.
Sure. So first, just to give a little background on it. So carbon pricing can mean either a carbon tax or some sort of cap and trade system where companies buy permits to emit certain amounts of greenhouse gases. Their goal is to provide a more level playing field across energy sources, which can help the cleaner ones scale up and be competitive. Because right now, a lot of the polluting sources cause a lot of damages, whether that's heart attacks and deaths from conventional pollutants or climate damages from greenhouse gases that are not reflected in their purchase price. So someone who goes to the hospital and pays medical bills or dies is clearly paying costs, but they're shouldering some of those costs on behalf of the businesses that are burning the fossil fuels. So carbon pricing should be thought of as a way of restoring fairness to the market and leveling the playing field across different technologies. It's not a way of providing an advantage to clean ones. In the United States and probably elsewhere too, some of the concerns with carbon pricing are, I guess there are two types of concern. One is about economic competitiveness of the businesses and leakage, and the other is about whether the carbon pricing is regressive or hurts low-income people who have to pay more for energy or energy-using services. And both of these can be overcome, and so I'll mention something about each of them in turn. So on the competitiveness front, you do want to pay attention to what's happening overseas. So you don't want to implement carbon pricing and then just have businesses immediately move overseas and ship products back to you after producing them with high emissions somewhere else, because that defeated the purpose. So one thing you need is ideally sort of multilateral agreement where you have carbon pricing across multiple jurisdictions. The more, the better. Another thing you can do is border adjustments. So if you have a product coming in from somewhere that's not part of your multilateral agreement and they don't have appropriate carbon pricing, you can use a tax as it enters your multilateral agreement zone or your country to increase its price so that it isn't cheaper than local producers' products and doesn't put your own domestic industry at a disadvantage. And similarly, to help your exports, you have to do the reverse when they're exporting out of the multilateral zone and give them a rebate on the carbon pricing, which is not ideal for the environment, but is part of what border adjustments are. So these considerations can help alleviate leakage. And then you can also try to do it, you can use the other policies like R&D support to make it cheaper to comply, cheaper to decarbonize. So if there's cheap zero carbon electricity available, that will help a lot. And the government can do that through a variety of ways that are a bit outside the domain of the electricity sector, like making it easier to permit and build renewables, building more transmission lines, even subsidies for the use of clean energy to industries, all that kind of thing can help. With the other concern is the one about sort of equity and disadvantaged people. So if you are a low-income family, you spend a greater percentage of your income on energy, whether that's fuel for your car or fuel for your home. And if it becomes more expensive, it has a disproportionate impact on people who have spent a higher percentage of their income on energy or energy using services like mobility. So my view is that the best way to deal with that is to use the revenues wisely. So one thing that's a big benefit of carbon pricing is that it generates revenue for the government that can then be put back into things that generate outsized benefits. So that could be R&D support, for example, where that clearly generates huge benefits per dollar. But you can also, for example, help fund public transit systems and make subsidized or free fare passes available to people who meet certain income requirements, who are not above a certain threshold, and then they get free mobility that is also carbon efficient. So rather than subsidizing the fuels themselves, like keeping gasoline cheaper, I'd rather find ways to use the money that provides equivalent or even better financial benefit for the impacted families, but not by making them pollute cheaply, but by just making other things cheaper. Mobility, food, even direct handouts or payments are all better than allowing them to pollute cheaper, because pollution is what we're trying to get rid of here.
Okay, so that was useful. Could we then move into looking at the green procurement issue? Because I think this speaks to one of the issues we hear a lot about from industry, which is where's the market for my low carbon product? You know, so tell us about your thoughts on this.
Sure. So green public procurement policies or programs are where the government either prioritizes or reserves the purchase of materials or products that were made with low life cycle carbon emissions, low embodied carbon emissions, or greenhouse gas emissions, really, not just carbon, literally. And that can be done by setting a standard for all government purchases or reserving a certain share. And it can also cover products and purchases that are partially funded by government. It doesn't have to be only things that government spent 100% bought in its entirety with no contribution of funds from any other source. So the purpose of this policy, the main purpose in my mind at least, is to give a starter market for companies that want to scale up. They have a new low carbon way of producing steel. They've built a pilot plant. They want to build more plants. They want to start converting over, but their price of that steel is not yet as low as the price of similar steel made through in a blast furnace and basic oxygen furnace. So if there's a buyer here, the government, the government funds a lot of projects like roads and bridges and infrastructure that consume a large quantity of steel and cement. So if the government funded projects like that prioritize low carbon steel, then you know you're going to have a buyer, and you feel the safety to build that factory, to scale up your pilot plant, to do 2 or 3 or 4 factories, because you have a market for your product. So it's really important to business, this type of policy, at least in the early stages before the cost comes down further, and also before there's sufficient standards or carbon pricing to make the product really viable in the general market. So you asked about where it's happening. One place in the United States that put in a policy like this is California. California has this Buy Clean initiative, where the state has set greenhouse gas limits per unit of product for various products, for products being like commodity materials that are purchased for government funded projects. I will caveat this, that the law didn't specify specific amounts of greenhouse gas. It said the state shall, set requirements through a, regulatory process, set the life cycle carbon limits. And the ones California came out with are too high. They're actually allow for products that are even worse than the industry average, meet the limits the agency that came out with these limits published. So that wasn't with the intent of the law. Fortunately, it can be fixed by the agency just issuing new guidance. It doesn't need a new law passed or anything. But it's a reminder that there's considerations both in how you design the legal text of the law, and then you need to make sure that the actual settings are meaningful and that truly focus on producible but green products. So certainly better than the industry average at the very least. The best place in the world that's doing this, I believe, is the Netherlands.
Let's come back round actually now to something that you talked about briefly at the beginning, which was your kind of the open source project, the Energy Policy Simulator, and the work that you've done there. So, I mean, obviously everything we've talked about here, it was all designed to be, to kind of point to this thing of that there are levers and buttons that can be pressed by both industry and by policymakers and by investors, and that what we need is the right kind of technology, the right technology supported by the right policy design. And my understanding is that that is what the simulator can help point to. So talk us through, how does that get used? What can people gain from from a use of that simulator?
Sure. So the simulator is so it's a powerful tool. It's free and open source, and anyone can access it. It's just energypolicy.solutions. So or www.energypolicy.solutions, same place. So that's easy to remember, the .solutions top level domain. And you can either run it online on that site in your browser, because we have it running interactively on a server, or you can download it. And if you download it, you can see all the input data. All of it is carefully cited and referenced. It's filled with public input data from governments and peer-reviewed publications and such. So what does it do? You can interactively test all kinds of different energy and climate policies and see what effect they would have on industry, as well as other parts of the economy, like the transport system or the electric power system. But for us, we're interested in industry. So the range of policies is enormous and includes many policies that would be implemented by the industry sector or binding on the industry sector itself. There's energy efficiency standards, there's industrial carbon capture, there's material efficiency standards, there's carbon pricing, there's all kinds of things in there that you can test, and you can set them to whatever level of stringency you want. So you can test a carbon price at $30 US per metric ton or $35 US per metric ton. The simulator runs from 2020 to 2050, and you can phase in the policies any way you want on that time frame. So you could have a carbon price that starts at 0 and ratchets in until reaching whatever your desired setting is in 2040, say, and then stays constant at that level through till 2050, or any other schedule you wish. So there's too much to this tool to explain it all now.
And especially in an audio podcast, because obviously, ideally, you'd have it on screen.
Yeah, that too. Fortunately, we do have videos. So if you go to energypolicy.solutions, one of the links you'll see there is to a button that says View EPS Video Series. And that gives you the visual version, which will walk you through the simulator and how it works. It's really compelling, great for podcast lovers, and you can play with it yourself on that site. I think it's a very useful tool, not just for policymakers, but also for industry to see what type of policies they might want to push for or advocate, and for advocates or interested people otherwise. It is a policy analysis tool, so it's not going to tell you about your specific business. What do I do if I invest in a new boiler? But there are other tools for that. This tool is pretty unique in its scope and capabilities and its maturity. So I encourage folks to check it out.
Well, just for anybody listening who's interested in that, definitely do have a look. And if you want the URL, you can either get in touch with us, or if you look on our website, you'll be able to find it in the show notes for this particular podcast as well. Well, Jeffrey, thank you so much. I feel like I have pulled a million bits of information out of your brain, but thank you for being so open and sharing, your perspective on this, but also the I guess all the experience that you're gaining by working with industry in this way. It's just been really interesting. Thank you so much.
Well, thank you. It's been a pleasure to be here and to share with your listeners. I enjoyed it.